Leonardo da Vinci is widely celebrated as a Renaissance man, someone who excelled in multiple areas and disciplines combining art, science, and engineering in ways that were way ahead of its time. As an artist, his famous works include timeless pieces like the Mona Lisa, The Last Supper. His artistic achievements are defined by a deep understanding of anatomy, light, form, and promoting realism and expressionism in art. Beyond his artistic genius, Da Vinci was an extraordinary observer of nature. His notebooks revealed detailed studies of plants, animals, and geological formations, showing a curiosity for understanding the intricate mechanisms of life. His botanical studies are particularly remarkable as he approached plants not just as objects for art, but as living systems.
Over 500 years ago, Leonardo da Vinci discovered what he believed to be a universal pattern among trees. In an effort to help fellow artists depict trees in their artwork, da Vinci proposed a rule to predict branching structures. His rule stated that all the branches of a tree at every stage of its height, when put together, are equal in thickness to the trunk below them. So in other words, the area of any given branch is equal to the area of all the daughter branches emerging from it. If it were graphed, this rule would reveal a linear relationship between the mother and daughter branches with a slope of 1.
But is Da Vinci's rule universal or even accurate? He formulated the rule of trees through careful observation of nature in the temperate environment of northern Italy where he lived and worked. These trees conform to his theories because they tend to grow in predictable patterns that maximize light capture in open spaces. Tropical trees, however, may vary as they grow in dense, competitive rainforests, where their structure is heavily influenced by the need to outcompete others for light. His observations were often shaped by the limits of his environment, tools, and knowledge at the time. With more basic instruments like quadrants and cross staffs, the principles of geometry, and a fair amount of estimation and guesswork.
The Wet Tropics World Heritage Site in Queensland contains one of the oldest surviving rainforests in the world. Some areas have been refugia over millions of years of climatic changes, acting as havens for species when areas farther inland have changed. There are many representations of diverse ancient plant families, especially of flowering plants. We visited sites with differing elevation and rainfall, including old-growth rainforests, revegetation forests, and suburban sites. This variety of families and range of evolutionary time allowed us to sample over 80 species from more than 50 families across the plant evolutionary tree.
So here in the wet tropics of Australia, we got some really interesting plants in the rainforest here. Like over here, we have this plant known as Eupomatia, and it is one of these, it belongs to a group of flowering plants which are one of the earliest branching lineages of flowering plants. Or in other words, some people consider them like some of the most ancient flowering plants that have appeared on land. And here we have what is known as a northern sassafras, and it belongs to a family of plants that is only found in the southern hemisphere. Or in other words, it has a Gondwanan legacy. So this is another reason why the rainforest of the wet tropics is so unique.
To first test Da Vinci's rule, our team set out to measure the diameters of mother and daughter branches. Tree or shrub, tall or short, wide or thin, we used a wide range of equipment like calipers, pruners, and ladders to gather a large collection of data. This allowed us to see firsthand how strategic, deliberate, and concise a tree's branching scheme really is, and more importantly, why it matters. Extreme weather events like droughts in the wet tropics are a massive contributor to tree mortality and forest death.
And the effects of global climate change has only made droughts more frequent in places like Australia, furthering the risk of tree mortality.
During droughts, plants close their stomata so that they don't lose more water. And because of this closing the stomata, it means that they do less photosynthesis. And doing that, they have less carbon as well to sustain the cells. Trees with daughter brains that have smaller total areas than the mother brains, which, by the way, don't follow the Da Vinci's rule, they need less carbon to sustain themselves, and then they are more tolerant to droughts.
We were able to compile our findings in the graph shown. The slope of this line created by this data is slightly less than 1. Ultimately, this reveals that while Da Vinci's rule may have been accurate for some plants, it cannot be applied universally, especially in the wet tropics. The graph also reveals a few outliers, which may be useful to investigate further.
Our investigation is part of a global research study on the relationship between mother and daughter branching across continents, led by Ana Isabel Perez Mason, a doctoral researcher at the National Autonomous University of Mexico.
When we find an outlier, the first step is to check the database. We also try to find that these values correspond to a specific taxon or if the individuals come from a particular location with unique environmental characters. So that's why our goal, conducting a broad study covering as much as phylogenetic diversity as possible. This allows us to create models that explain most of the cases and develop general management plans and to address challenges like massive mortality during drought.
Understanding the accuracy of Da Vinci's rule and the simple relationship between mother and daughter branches can aid an expert's knowledge of the causes of mass tree mortality during drought.
As climate change progresses, this will assist conservationists in protecting trees against the processes that will harm them first, as they support all life in the forest.